The Milky Way is, by any standard a person can practically relate to, an incomprehensibly large object. It stretches roughly 100,000 light-years from one edge to the other. It contains somewhere between 200 and 400 billion stars. A beam of light leaving one side of it would take 100,000 years to reach the other side, and that light never slows down. The solar system, our sun and all the planets orbiting it, sits roughly 26,000 light-years from the galactic center. If you try to drive to the center of the Milky Way at highway speed, ignoring everything about the laws of physics that make that impossible, you would still be driving more than 1 billion years from now. By the scales we use to measure things in daily life, the Milky Way is effectively infinite, and it is one of the most average-sized galaxies there is. Among the estimated 2 trillion galaxies in the observable universe, the Milky Way is somewhere in the middle, larger than the swarms of dwarf galaxies that make up the majority of galactic objects, but dwarfed in turn by a class of structures so enormous that placing the Milky Way next to them is like holding a coin next to a continent. And size alone barely captures the full picture, because some of the universe's most extraordinary galaxies aren't just record-breakingly large. They are deeply, genuinely strange, objects that astronomers have been studying for decades and still cannot fully explain. Objects whose very existence exposes cracks in the most carefully constructed models of how the universe is supposed to work. The universe is not a uniform place. It builds things at extremes. Some of the extremes are extremes of mass and physical scale, structures so large that human intuition fails completely in trying to picture them. Others are extremes of strangeness, objects that look like nothing in the textbooks, behave in ways no simulation predicted, and resist explanation through every theoretical framework that has been applied to them. Still others are extremes of time, galaxies that appear to have formed too fast, grown too massive, or organized themselves into mature structures in an era when the universe was supposed to be too young for any of that to be possible. What a galaxy is, and why measuring one is harder than it sounds. Before getting into the extremes, it's worth pausing on what a galaxy actually is, and why measuring one turns out to be surprisingly complicated. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter, the invisible substance that makes up most of a galaxy's total mass and does not interact with light, only with gravity. What holds everything together is gravity. Without it, the stars would disperse into the surrounding void over time. At the center of nearly every large galaxy sits a supermassive black hole, ranging in mass from millions to tens of billions of times the mass of our Sun. Around that center, stars orbit in patterns that depend on how the galaxy formed, flat, rotating disks with spiral arms in spiral galaxies, rounded, featureless clouds in elliptical galaxies, and irregular, disturbed shapes in galaxies that have recently collided with or been disrupted by a neighbor. Galaxies also don't live in isolation, they cluster. The Milky Way is part of the Local Group, a collection of roughly 50 galaxies dominated by the Milky Way and Andromeda, spanning about 10 million light-years. The Local Group is itself part of the Virgo supercluster, which is part of an even larger structure called Laniakea, a gravitationally connected web of galaxy clusters spanning 520 million light-years. This hierarchical clustering means that the largest galaxies are almost always found at the gravitational centers of the largest clusters, where matter has had the longest time and the best conditions to accumulate. This is not a coincidence, it's a fundamental consequence of how gravity works across cosmic time. Now, measuring a galaxy's size sounds like it should be simple. You point a telescope at it, measure how wide it appears in the sky, factor in the distance, and get a diameter. The problem is that galaxies don't have clean edges, they fade. Stars become more and more sparse as you move outward from the center until the galaxy's glow drops below whatever sensitivity threshold your telescope has. A more powerful instrument or a longer exposure often reveals that a galaxy extends further than previously catalogued, sometimes dramatically further, when extremely faint outer halos of old stars are detected for the first time. Some galaxies have been found to have halos that extend 2 or 3 times further than the previously measured radius, once a sensitive enough instrument was pointed at them. This means that the question of which galaxy is the largest depends significantly on how you define the boundary. If you measure to where most of the bright stars end, you get one number. If you include the diffuse outer halo of aging stars that surrounds many large galaxies, you often get something much bigger. And if you include the jets of plasma some galaxies fire into intergalactic space, massive structures produced by supermassive black holes that can extend millions of light years in every direction, the numbers become almost surreal. Each definition captures something real about the galaxy, and each emphasizes a different aspect of how it formed and evolved. A galaxy's bright core tells you about its current star formation and central concentration. Its extended halo tells you about its merger history. Stars stripped from absorbed galaxies settle into wide, spread out orbits that build up the halo over billions of years. Its radio lobes, where present, tell you about its central black hole's activity and the properties of the surrounding intergalactic medium. Different galaxies hold different records under different definitions, and the full picture of any individual galaxy requires understanding which measurement you're making and what it reveals. What follows is an exploration of the records held under each definition, and then of the galaxies that hold a different kind of record entirely, the ones that are the most scientifically challenging to understand. IC1101, the galaxy that swallowed 1,000 others. By the measure of stellar mass, the total number of stars contained within a single gravitationally bound structure, the record belongs to IC1101. IC1101 sits at the center of a galaxy cluster called Abell 2029, roughly 1.04 billion light-years from Earth in the direction of the constellation Virgo. It was first catalogued in the late 1800s by William Herschel, the same astronomer who discovered Uranus, though at that time it appeared as little more than a faint smudge and was assigned no special significance. The galaxy's true scale only became apparent through systematic study over the following century, and each generation of instruments revealed something more extreme than the last. The bright central core of IC1101 spans somewhere between 400,000 and 550,000 light-years, depending on the measurement band used, 4 to 5 times the diameter of the entire Milky Way, just in the core region. But the core is only the beginning. Surrounding it is an enormous, diffuse halo of older stars extending outward to a radius of roughly 2 million light-years. From one edge of that halo to the other, IC1101 spans approximately 4 to 6 million light-years, depending on how far out into the halo you trace the starlight. To anchor that number in something familiar, the distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. The stellar halo of IC1101 is wider than that entire gap. If the Milky Way were replaced by IC1101, its stars would extend well past Andromeda, covering the space between us and most of the other nearby galaxies in every direction. Inside that structure live an estimated 100 trillion stars. The Milky Way, with its 200 to 400 billion, is outclassed by a factor of roughly 300. The total mass of IC1101's visible stellar content is estimated at close to a quadrillion times the mass of the Sun, a 1 followed by 15 zeros. The dark matter halo surrounding and permeating the galaxy adds significantly to that figure, though the precise total mass of the dark matter component is harder to constrain. IC1101 grew this way through one of the most effective processes the universe has on offer: cannibalism. It is what astronomers call a brightest cluster galaxy, one of a class of objects that form at the gravitational center of large galaxy clusters and grow by repeatedly absorbing the other galaxies in the cluster over billions of years. Each galaxy that falls too close gets torn apart by tidal forces or swallowed in a full merger. Its stars, gas, and dark matter are stripped away and incorporated into the central mass. Every merger adds new material, but the dynamics of large mergers also transfer kinetic energy into the system, which tends to heat and spread the absorbed stars rather than compressing them toward the center. This is why IC1101's halo is so much larger than its core. It is built primarily from stars stripped out of hundreds or thousands of absorbed galaxies, redistributed into wide, loose orbits far from the center. At the very core of IC1101 sits a black hole with an estimated mass between 40 and 100 billion times the mass of the Sun, placing it in the category of ultramassive black holes, a designation reserved for the extreme upper end of what black holes appear to be able to achieve. For comparison, the black hole at the center of the Milky Way weighs about 4 million solar masses. IC1101's black hole outweighs it by a factor of somewhere between 10,000 and 25,000. Even at the lower end of the estimated range, it is among the most massive black holes ever identified anywhere in the observable universe. There is also something unusual about IC1101's core that becomes apparent when examined closely. Most large elliptical galaxies have a dense packing of stars right at the center, clustered tightly around the central black hole. IC1101's core is the largest known in any galaxy, estimated at a radius of about 14,000 light-years. But it is strangely dim for something that size. There are far fewer stars there than expected. The leading explanation is that this is the scar left by repeated black hole mergers over the course of IC1101's growth, when two galaxies collide and the central black holes spiral in toward each other and eventually merge. The inspiral process releases energy that slings surrounding stars outward in a kind of gravitational shockwave. Over many successive mergers, and IC1101 has had many, this process gradually excavates the central region, expelling stars into the halo. The estimated stellar mass deficit in IC1101's core, the amount of material that should be there based on the core size but isn't, is roughly 500 billion solar masses. That missing mass was thrown outward, merging into the halo during billions of years of black hole in spiral events. Despite containing 100 trillion stars, IC1101 is essentially a dying galaxy. The star formation has all but stopped. The galaxy stars are predominantly old and metal-rich. Most of them formed more than 7 billion years ago, giving the galaxy a warm golden color in detailed imaging. Almost no cold gas remains. Gas is the fuel for new star formation, and IC1101 has consumed or expelled nearly all of it. The stars will age, grow dim, and eventually leave behind white dwarfs, neutron stars, and stellar mass black holes over the coming tens of billions of years. Meanwhile, IC1101 will continue slowly growing, absorbing whatever remaining galaxies enable 2029 wander too close, but gaining only more old stellar populations, no new bursts of star birth. It will become larger in mass and smaller in luminosity simultaneously, gradually darkening as the last of its original stellar population burns out. In the very far future, tens of trillions of years from now, in a universe far older and colder than the one we inhabit, IC1101 will likely be one of the last structures of any significant size still standing. The accelerating expansion of the universe will have carried every other galaxy cluster beyond its gravitational reach by then, leaving IC1101 alone in an otherwise dark and empty region of space-time, the last remnant of its cluster's billions of years of assembly. Whatever was impressive about it will have faded to darkness long before any observer capable of appreciating it could survive to witness it. But as a record of what gravity can accomplish given time, material, and a good position in the cosmic web, IC1101 is unlikely to be surpassed. Alcyonius, the galaxy whose black hole redrew the map. For years, IC1101 was the answer to the question of which galaxy is the largest. Then, in 2022, astronomers looking through radio telescope data found something that required the question to be asked again and answered differently. The galaxy is called Alcyonius, named after a giant from Greek mythology, one of the gigantes who battled the Olympians, described as immortal within the bounds of his homeland. It sits about 3 billion light-years from Earth in the constellation Lynx, and at its center it is, in most respects, an unremarkable elliptical galaxy. Its total stellar mass is estimated at roughly 240 billion solar masses, less than half the mass of the Milky Way. Its central black hole is approximately 400 million solar masses, which is substantial but modest compared to the most extreme cases known. Its radioluminosity, the total power it is pumping out in radio waves, is, by the standards of radio galaxies, average. By the most conventional measures of galactic significance, Alcyonius is unexceptional, but its black hole has done something that no other known galaxy's black hole has managed to do. To understand what makes Alcyonius so extraordinary, it helps to understand how radio galaxies work in general. When a supermassive black hole is actively consuming material, such as gas, dust, and stars. Some of that infalling matter doesn't make it into the black hole. Instead, magnetic fields near the black hole can redirect a fraction of the infalling material and accelerate it outward along the black hole's rotation axis, creating two jets of plasma moving at close to the speed of light in opposite directions. These jets are not physical tubes of material in the usual sense. They are channels of plasma confined by magnetic fields, maintaining their coherence over extraordinary distances as they punch first through the galaxy itself and then out into intergalactic space. As the jets travel outward, they push against the thin gas that fills intergalactic space. Eventually, after traveling hundreds of thousands or millions of light years, the pressure of the surrounding medium wins, and the jet can no longer maintain its collimated structure. The plasma spreads out and slows, inflating enormous lobes of radio-emitting material, vast bubbles of charged particles and magnetic field that can persist for hundreds of millions of years, glowing in radio wavelengths as their particles spiral around magnetic field lines. This is what makes radio galaxies visible to radio telescopes. Not their stars, not their central engines, but these enormous structures of plasma that extend far beyond the visible galaxy itself. Most large radio galaxies have lobes spanning a few 100,000 to a few million light years. These are themselves tremendous structures, far larger than the visible galaxy that produced them. Some of the most celebrated examples in astronomy, like Hercules A, have lobes spanning hundreds of thousands of light years, while the visible galaxy they surround is only a tiny fraction of that. The lobes of Alcyonius span 16 million light years from tip to tip. That is 16 million light years. The entire local group of galaxies, the collection containing the Milky Way, Andromeda, and every small companion and satellite galaxy associated with either of them, spans roughly 10 million light years. Alcyonius, end to end, is larger than the galaxy group we live in. It is about 160 times the diameter of the Milky Way. The discovery was made by a team led by Martijn O at Leiden Observatory in the Netherlands, working through data from LOFAR, or the Low Frequency Array, a network of roughly 20,000 individual radio antennas spread across Europe and connected together to function as a single enormous telescope. LOFAR's particular strength is sensitivity in the low-frequency radio band, frequencies below what conventional radio observatory arrays can reach with comparable depth. The plasma lobes of giant radio galaxies emit preferentially at these lower frequencies, and the combination of LOFAR's frequency coverage and its sensitivity to extended, low-brightness structures made it possible to see Alcyonius's lobes for the first time, even though the galaxy itself had been catalogued for decades. What puzzles scientists most is the stark mismatch between the size of those lobes and the apparent ordinariness of what produced them. In their published paper, OA's team noted explicitly that the stellar mass, black hole mass, and radioluminosity of Alcyonius are all below the median for giant radio galaxies as a class. Not only is the central galaxy unremarkable, it is, by the most relevant metrics, slightly below average. The team concluded that neither a very massive galaxy nor a very powerful central black hole appears to be necessary to grow lobes at this scale. Two hypotheses are currently being investigated. The first is that the intergalactic medium surrounding Alcyonius may be unusually underdense, containing less gas than typical for its environment. If the jets are expanding into a particularly empty region, they encounter less resistance and can grow larger before stalling, in the same way that a bubble blown into vacuum expands further than one blown in water. The second hypothesis is that Alcyoneus sits inside a cosmic filament, one of the vast threads of gas and dark matter that connect galaxy clusters across the universe, and that the geometry of this filament channels the lobe expansion in a preferred direction, reducing the effective resistance the jets encounter. Neither explanation has yet been confirmed. Future surveys may be able to map the density structure of the intergalactic environment around Alcyoneus with enough precision to distinguish between them. Rubin's galaxy, the gentle giant nobody can fully explain. Among spiral galaxies specifically, the organized rotating disk galaxies with spiral arms, one of the largest known examples, sits about 232 million light-years away in the constellation Perseus. Its official name is UGC 2885, but astronomers now call it Rubin's Galaxy, in honor of the physicist whose work on it helped transform our understanding of the universe. Vera Rubin spent much of her career in the 1960s, 70s and 80s measuring the rotational properties of spiral galaxies, and what she found was deeply unsettling. Stars in the outer regions of spiral galaxies were moving far faster than they should, based on the amount of visible mass present. In our solar system, the outer planets orbit the Sun more slowly than the inner ones because the Sun's gravity weakens with distance. By analogy, the outermost stars of a spiral galaxy should orbit more slowly than the inner ones. Instead, the rotation curves of spiral galaxies were flat, meaning outer stars were moving at roughly the same speed as inner ones, regardless of how far from the center they were. The only explanation that worked was the presence of a large, invisible mass distributed throughout and around the galaxy, dark matter. Rubin's rotation curve measurements on dozens of galaxies, including what we now call Rubin's Galaxy, built the foundation of observational evidence that made dark matter's existence broadly accepted in modern cosmology. She was nominated for the Nobel Prize multiple times and never received it. She died in 2016, and the Nobel is not awarded posthumously. The naming of this galaxy in her honor was announced in 2020 at a meeting of the American Astronomical Society by Benna Holwerda of the University of Louisville, who proposed the name specifically to acknowledge that Rubin had been studying UGC 2885 for decades, and that the galaxy had been a key part of the dataset that supported her most important discovery. In the same year, the Large Synoptic Survey Telescope in Chile, a major new observatory that will survey the entire visible sky repeatedly, was renamed the Vera C. Rubin Observatory. These recognitions, however overdue, reflect a debt the field acknowledges it owes. Rubin's galaxy itself stretches about 438,000 light-years across, roughly 4 times the diameter of the Milky Way. It contains approximately 1 trillion stars, nearly 3 times the Milky Way's estimated stellar content. Holwerda described it at the AAS meeting as potentially the largest known spiral galaxy in the local universe, and noted that it is about as large as you can make a disk galaxy without it having collided with something. That last observation is the mystery. Galaxies grow to enormous sizes through mergers. 2 galaxies collide, interact gravitationally, tear each other's disk structures apart, and eventually settle into a larger combined system. This process leaves characteristic traces: disturbed spiral arms, tidal tails stretching away like cosmic streamers, populations of star clusters with orbital properties inconsistent with the main disk, and often bursts of intense star formation triggered by the merger's compression of gas clouds. Very large spiral galaxies typically show at least some evidence of this kind of history. Rubin's galaxy shows almost none of this. Its spiral arms are smooth and undisturbed. There are no tidal tails. Its central black hole is dormant, producing no jets, no active accretion disk, no signs of being fed by infalling material from a recently absorbed companion. Its rate of star formation is below average for a galaxy its size, roughly half the rate of the Milky Way, which is itself not an especially prolific star-forming galaxy. Everything about it is quiet and isolated, not massive and merged. The current best explanation is accretion from the cosmic web. Rubin's galaxy appears to be located in a region where cosmic filaments, the vast web-like threads of gas and dark matter that connect galaxy clusters across the universe, have fed it steadily over billions of years. Rather than growing through violent, episodic mergers, it built itself slowly through the steady infall of intergalactic hydrogen gas, converting it into new stars at a low but continuous rate that maintained the disk's structure while gradually building up its mass. Holwerda's team has been studying the galaxy's globular cluster population to test this picture. Galaxies that grow primarily through mergers end up with globular cluster populations that are larger than expected for their current mass. They've stolen the clusters of every galaxy they absorbed. Galaxies that grow primarily through gas accretion have cluster populations more proportional to what they formed in-house. The analysis is ongoing, but the current evidence favors the quiet accretion history over a merger-heavy one. Rubin's galaxy may be the universe's demonstration that, given enough time and a sufficiently well-supplied cosmic environment, a spiral galaxy can grow to truly enormous scales without ever having to collide with another large galaxy at all. That is either impressive discipline or extraordinary luck, and distinguishing between them is part of what future observations aim to determine. Marlin 1, the galaxy that hid for 60 years. Not every large galaxy is hard to miss. Some are invisible, not because they're far away, but because they're so extraordinarily faint that no telescope built in the 20th century was capable of detecting them. The most spectacular example was found hiding in sky survey photographs that had existed for decades before anyone had the right technique to notice what was in them. Marlin 1 is located about 1.2 billion light-years away in the constellation Coma Berenices. It was discovered in 1986 by astronomer David Marlin, who had developed specialized photographic processing techniques for stacking and chemically intensifying telescope plates to pull extremely faint structures out of background noise. Methods that were unlike anything being used elsewhere in observational astronomy at the time. Running these techniques on archival survey data, Marlin noticed a ghostly, enormous structure that had been present in the photographs all along and simply gone unrecognized. What he found was a spiral galaxy with a disk stretching roughly 650,000 light-years across, up to 750,000 light-years by some later measurements, placing it at 6 to 7 times the physical diameter of the Milky Way. It is almost invisible. The stars in Malin 1 are distributed so sparsely across such a vast area that the surface brightness of its disk, the amount of light it emits per unit of apparent area on the sky, falls far below the threshold that conventional telescopes and standard imaging techniques were calibrated to detect. The problem is not a shortage of stars. There are stars, vast numbers of them, distributed across an area so enormous that the stellar density per square unit of disk area is extraordinarily low. In deep images of the galaxy's core region, you can see other, more distant galaxies shining through Malin 1's disk from behind, visible through the gaps between stars in much the same way you can see through a very thin fog. It is, in the most literal sense, a see-through galaxy. The structure of Malin 1 reveals something unusual when examined in detail. At the center of the enormous ghostly outer disk is a relatively compact and ordinary-looking barred spiral, a core spanning about 30,000 light-years with a central bulge, a bar, and a small inner disk that would be considered unremarkable if it existed on its own. This inner structure could pass as a perfectly standard galaxy. The vast, diffuse outer disk surrounding it is a structurally distinct component, so different in character that the galaxy effectively contains two nested systems with entirely different properties. The leading explanation for how Malin 1 achieved this configuration involves angular momentum, the rotational energy stored in infalling gas during galaxy formation. If the gas that built Malin 1's outer disk had an unusually large amount of rotational energy compared to typical galaxy-forming gas clouds, it would have settled into orbits at much greater distances from the center than normal, spreading thinly over a far larger area rather than concentrating into a compact disk. High angular momentum gas forms large sparse disks. Over billions of years, the result would be exactly what Malin 1 shows, an enormous outer disk, too diffuse to form stars efficiently, wrapped around a more compact inner galaxy. Star formation in the outer disk proceeds at an almost geological pace. The gas density across most of the disk's area falls below the threshold required for efficient gravitational collapse into new stars. Observations using the Very Large Telescope in Chile have detected the emission signature of ionized hydrogen in scattered pockets across the outer disk, confirming that some star formation is occurring. But the rate is far below what the physical extent of the disk would suggest. The galaxy is building itself in the outer regions, but so slowly that it could be billions of years before the outer disk develops a significant stellar population. Malin 1 also requires enormous amounts of dark matter to explain its rotation curve. Like the normal spiral galaxies Vera Rubin studied, Malin 1's outermost visible regions rotate at speeds that the visible matter alone cannot explain. The dark matter halo must be correspondingly immense, extended far beyond even the enormous outer disk. The total mass of the system, including all the dark matter, is estimated to be comparable to or greater than the Milky Way's total mass, despite containing far fewer stars per unit volume. Most of Malin 1's mass is dark and invisible, as it is in all large galaxies, but the extreme ratio of invisible to visible material is particularly striking given the galaxy's vast physical extent. The deeper importance of Malin 1's discovery was what it implied about everything astronomers had been missing. Before 1986, the standard assumption was that any galaxy large enough to be scientifically significant would be bright enough to appear in existing catalogs. Surveys were calibrated for normal surface brightness objects, and science programs were designed accordingly. Marlin once showed that assumption was wrong. An entire class of galaxy, physically enormous, cosmologically significant, but nearly invisible, had been hiding from every survey ever conducted simply because none of those surveys were optimized to find it. The discovery triggered a surge. In the following years and decades, astronomers developed new imaging techniques and survey strategies specifically aimed at low surface brightness objects. Dozens of similar galaxies were eventually identified. The Dragonfly telephoto array, which later found NGC1052-DF2, was designed precisely to detect objects in this class. The surveys continue to reveal new examples as imaging technology improves. There may be many more Marlin 1 scale structures out there in the space between the galaxies we can see, waiting for the next person to develop the right technique and look in the right direction. Hoag's object, the galaxy nobody can explain. In 1950, astronomer Arthur Hoag was reviewing photographic plates from a sky survey when he came across something that stopped him. At first, it looked like a planetary nebula, a ring of glowing gas expelled by a dying star. A common enough object in galaxy surveys, but the distance measurements didn't match. It was far too remote and far too large to be anything of the sort. Spectroscopic analysis confirmed it was extragalactic. Further study confirmed it was a galaxy. But no one could explain what kind of galaxy it was, and more than 70 years later, that remains the situation. Hoag's object sits about 600 million light-years away in the constellation Serpens. It spans roughly 100,000 to 120,000 light-years across, comparable in physical size to the Milky Way. It contains an estimated 8 billion stars, and it looks, in detailed Hubble images, like a perfect ring of brilliant blue stars floating in space around a dense, round ball of old red stars, with a dark gap between them that contains almost nothing at all. The outer ring is made of young, hot, recently formed stars. The central nucleus is an ancient quiescent spheroid. The gap between them is essentially empty. Nothing connects the two. No spiral arms, no bars, no streams of stars bridging the space. Just a nucleus, a void, and a ring with perfect circular symmetry. The most common explanation for ring-shaped galaxies is a head-on collision. A smaller galaxy passes directly through the center of a larger, gas-rich disk, sending a density wave rippling outward like the rings that spread from a stone dropped in water. As the wave expands, it compresses gas and triggers star formation along its outer edge, creating a ring of young stars. The galaxy that caused the impact then continues on its way, leaving the ring structure behind. This mechanism is well understood and well documented. The Cartwheel Galaxy, one of the most photographed ring structures in astronomy, is a classic example, and the smaller galaxy responsible for it is still visible nearby, trailing away from the collision. In Hoag's object, there is no second galaxy, no traces of the projectile that would have triggered the ring. No tidal debris in the surrounding space, no stellar streams pointing in the direction of a retreating intruder, no faint elongations in the nucleus that might indicate an off-center impact. Radio observations have confirmed that no major galaxy-to-galaxy interaction has occurred in at least the past billion years. If a collision started a structure, it happened so long ago that every piece of evidence has been erased, which is itself deeply unusual. Galactic interactions typically leave detectable traces for several billion years. A second explanation proposes that Hoag's object was once a barred spiral galaxy and that its internal structure became unstable over time. In a barred spiral, the bar at the center drives gravitational resonances that can push material outward through the disk. Under certain conditions, this can produce a ring structure. It's a process called secular evolution, driven by the galaxy's own internal dynamics rather than an external event. This has been observed in other galaxies to varying degrees, but the nucleus of Hoag's object is spheroidal, not disk-like. Barred spirals have disk-shaped nuclei. The barred dissolution scenario, even if it could produce the ring, leaves the nucleus looking wrong, and the researchers who first seriously investigated this explanation concluded that the evidence for it was too thin to support a confident conclusion in either direction. There is one additional detail that makes Hoag's object even stranger to look at. In the dark gap between the outer ring and the central nucleus, at roughly the 7 o'clock position, there is a small smudge visible in the deepest Hubble images. That smudge is another ring galaxy, far more distant, seen in the background through the gap of Hoag's object. A ring galaxy embedded in the gap of another ring galaxy. The probability of this particular alignment occurring by chance along any arbitrary line of sight is very small. Whether it has any physical significance for Hoag's object itself is debated. Most astronomers treat it as a remarkable coincidence, but it adds one more surreal layer to a galaxy that is already without peer. Hoag's object remains the only galaxy of its kind in the sense that matters most, perfectly circular with the exact combination of outer ring, empty gap, and spherical nucleus that defines it. Other so-called Hoag-type galaxies exist, but all of them have elongated or barred nuclei, or show faint traces of spiral structure, or are imperfect in their symmetry in ways that allow existing models to at least partially account for them. Hoag's object, after more than 70 years of study, does not. What makes this especially interesting is that Hoag's object has not been ignored. It is one of the most photographed and studied unusual galaxies in modern astronomy. It received full Hubble imaging in 2001. It was re-examined with AI process denoising by Hubble's archive team in 2024, producing cleaner images than had ever been available. The wider neutral hydrogen distribution around it has been mapped with radio telescopes, which found it extends beyond the visible ring. Its stellar populations have been analyzed spectroscopically. Every major technique available to modern astronomy has been applied. The answer has consistently been the same. We do not know. Arthur Hoag himself, in the brief note announcing his discovery, wrote that a proper classification would be a worthwhile short-term project. That short-term project has now lasted 75 years. Hoag died in 1993, having seen the problem get more refined but not solved. It will likely remain unsolved until either some future observation reveals evidence that previous instruments were unable to detect, or a computational model is developed that can reproduce the specific combination of features, the perfect ring, the empty gap, the spherical nucleus, without requiring a set of initial conditions so precisely contrived that they amount to no explanation at all. NGC1277, a messenger from the early universe that somehow survived. Not all of the universe's mysteries involve objects that are physically enormous. Some of the most scientifically significant galaxies are strange precisely because of how unchanged they are, because they appear to be fragments of the early universe that somehow survived intact into the present day, fossils in a cosmos that typically destroys or transforms everything. NGC1277 sits about 240 million light-years away in the Perseus galaxy cluster. Physically, it is tiny by the standards of the objects discussed so far. Its effective radius is only about 4,000 light-years, making it roughly 1/4 the physical size of the Milky Way. It has about twice the Milky Way's total stellar mass packed into that small volume, making it extraordinarily dense, and every single star in it, as far as astronomers can tell, formed more than 10 billion years ago. Not most of the stars, not the majority, all of them. Since that initial burst of star formation ended, NGC1277 appears not to have changed at all. Galaxies like this are called relic galaxies, compact, dense, ancient objects that formed rapidly in the early universe and then, for reasons that vary by case, stopped evolving. In the early universe, roughly 10 to 13 billion years ago, very compact massive galaxies were common. They formed quickly, burned through their gas in furious early episodes of star formation, and then quenched. Over time, most of them grew and evolved, merging with other galaxies, accreting new material, building up extended outer envelopes of stars, and gradually transforming into the larger, more spread out ellipticals that dominate galaxy clusters today. The compact originals were effectively swallowed by their own growth. Only about 1 in 1,000 massive galaxies is expected to have survived this transformation process intact, remaining today in essentially the same compact form it had more than 10 billion years ago. NGC1277 is one of those rare survivors, and what has preserved it is its peculiar situation inside the Perseus cluster. The galaxy is moving through the cluster at roughly 2 million miles per hour, fast enough that it cannot slow down, merge with other cluster members, or accrete significant amounts of new material. Every time it sweeps close to another galaxy, the encounter is too brief and the relative velocity too high for a true merger to occur. Meanwhile, the hot intergalactic gas that fills the Perseus cluster is so energetically heated by the cluster's gravitational well that it cannot cool enough to collapse and form new stars. NGC1277 is effectively frozen, surrounded by material but unable to use any of it, moving too fast to accumulate anything new, preserved by the very dynamic environment that might have destroyed a slower, less lucky galaxy. Astronomers have confirmed NGC1277's status as a relic galaxy through a specific observational signature: its globular clusters. Large galaxies typically have two populations of globular clusters around them: red ones, which form during the galaxy's initial assembly, and blue ones, which arrive later as the galaxy absorbs smaller companion galaxies, whose globular clusters get stripped away and incorporated into the halo. The ratio of red to blue globular clusters therefore reflects a galaxy's accretion history. Galaxies that have been merging and growing have both kinds. The Milky Way has roughly equal populations of each. NGC1277 has almost exclusively red ones. The absence of blue globular clusters is direct evidence that the galaxy has not consumed any smaller galaxies since its initial formation. It has been in effective isolation, developmentally speaking, for 10 billion years. This makes NGC 1277 scientifically extraordinary. It is, in the phrase astronomers use, a window into the early universe, a rare example of a galaxy that shows exactly what the compact, dense, rapidly formed objects of the early cosmos looked like before most of them were transformed beyond recognition by mergers and accretion. Everything that standard surveys observe in the early universe, the compact red and dead galaxies that show up as faint red dots at extreme distances in JWST and Hubble Deep Field images, is of the same type as NGC 1277, but those are so far away that even JWST can only see them as unresolved points of light. NGC 1277 is close enough to study in detail. Its individual stars can be resolved, its globular cluster populations can be categorized, and its internal velocity structure can be mapped. It is the only object of its kind within practical observing range. The fact that NGC 1277 also has an anomalously massive central black hole, with estimates ranging from a few billion to possibly tens of billions of solar masses, making it disproportionately large relative to the galaxy's total stellar mass, adds another puzzle. Most galaxies follow a fairly tight relationship between the mass of their central black hole and the mass of their stellar bulge. Larger bulges host larger black holes in predictable proportion. NGC 1277's black hole is far too massive for its host galaxy by this standard, which suggests that the black hole and the galaxy grew together in conditions very different from what is typical today. In the extreme density and turbulence of the early universe, with gas raining in from all directions at high rates, both the stars and the central black hole may have grown simultaneously and rapidly, in proportions that no longer occur in the calmer present-day cosmos. NGC 1277 is, in the most literal sense, an artifact from a different era of the universe, preserved by a fortunate combination of speed, environment, and isolation in the middle of a cluster that would have transformed most other galaxies beyond recognition. There is one final detail about NGC 1277 worth noting. The same kind of compact, dense, ancient galaxy that NGC 1277 represents locally, the compact red and dead galaxies of the early universe, is exactly what instruments like the James Webb Space Telescope are finding in large numbers at extreme distances. ZF-UDS-7329, the overmassive early quenching galaxy that has challenged cosmological models, may be a direct ancestor of objects like NGC 1277. It formed fast, accumulated an enormous stellar mass, shut down its star formation within the first billion years of the universe, and then, depending on where it ended up, either got absorbed into a larger galaxy over time or survived in a form close to what it was at birth. Studying NGC 1277 in detail therefore tells us things about those distant early universe objects that no other technique can provide. It bridges the gap between the early cosmos and the present day in a way that is scientifically unique. NGC 1052-DF2 and Dragonfly 44, two galaxies at opposite extremes of an impossible spectrum. One of the most firmly held beliefs in modern astronomy is that dark matter and galaxies are inseparable. You simply cannot have one without the other. Dark matter accounts for roughly 85% of all matter in the universe. Without it, the slight overdensities in the early universe would never have had enough gravitational pull to collapse and form galaxies at all. Standard models of galaxy formation begin with dark matter halos, vast invisible clouds of this substance, and treat ordinary visible matter as something that falls into those halos and forms stars. Galaxies are thought to be embedded in dark matter from the very start, and their dark matter halos are typically many times more massive than the visible galaxy inside them. In 2018, Peter van Dokkum of Yale University published a paper in Nature describing a galaxy that had, by all measurable evidence, almost none. Van Dokkum's team discovered the galaxy using the Dragonfly telephoto array, a custom-built telescope system unlike anything in conventional observational astronomy. Rather than using a large primary mirror as conventional telescopes do, Dragonfly uses an array of commercial telephoto camera lenses arranged to function together, a design that dramatically reduces the internal scattered light that blinds conventional telescopes to extremely faint, diffuse objects. It was built specifically to find the low surface brightness structures that standard instruments miss. NGC1052-DF2 was one of its first spectacular finds. The galaxy sits about 65 million light-years away in the constellation Cetus. It is physically large, roughly the diameter of the Milky Way, but contains only about 1/200th as many stars, making its disk so sparse that background galaxies are visible, shining right through it from behind. Van Dokkum's description of first seeing it in a Hubble image captured the strangeness well. A gigantic blob, so sparse you can see the galaxies behind it, literally transparent at cosmological distances. To determine how much dark matter it contains, the team measured the orbital speeds of 10 globular clusters orbiting in the galaxy's outer regions. The principle is straightforward. An object's orbital speed around a galaxy depends on how much total mass, visible and invisible combined, is enclosed within its orbit. More mass means faster orbits. If a galaxy has a substantial dark matter component distributed through and around it, the outer objects will move significantly faster than the visible stars alone can explain. This was the fundamental observation behind Vera Rubin's dark matter discovery, applied now to a very different kind of object. The globular clusters in NGC1052-DF2 were moving too slowly. The speeds were consistent with the gravitational force of the visible stars alone. There was no detectable additional mass from dark matter. Van Dokkum's team concluded the galaxy contains at most 1/400th the dark matter predicted by standard models for a galaxy of its size, and possibly none at all. The reaction from the astronomical community was intense. The claim was extraordinary, the first known galaxy lacking dark matter, and it attracted fierce scrutiny. Several groups challenged the distance measurement, arguing that if the galaxy was significantly closer than claimed, it would be smaller and less massive, and the apparent dark matter deficit would become unremarkable. A team from the Canarias Astrophysics Institute concluded the galaxy might be as close as 42 million light-years, not 65, which would restore a more normal dark matter fraction. The debate lasted years and involved some of the most prominent galaxy scientists working. In 2021, Hubble observations using red giant stars, which reach a precisely calibrated peak brightness across the universe, making them reliable distance markers, confirm the distance at approximately 65 million light-years. The deficit is real. One of the most important implications Van Dokkum's team drew was not that dark matter doesn't exist, but precisely the opposite. If dark matter were actually just a modification to how gravity behaves at low accelerations, as some alternative theories propose, then it would appear in every galaxy as a universal effect. A galaxy genuinely lacking dark matter would be impossible in those models. The existence of NGC 1052-DF2 therefore implies that dark matter is a real, separable, physical substance, not a property of gravity, something that can be present in some galaxies and absent from others, which is exactly what you'd expect from a particle that interacts with ordinary matter only gravitationally and can therefore be separated from it under the right conditions. The most likely separation mechanism is tidal stripping by the nearby massive elliptical NGC 1052. The gravitational differential of that large neighbor pulling harder on the near side of NGC 1052-DF2 than the far side may have gradually stripped away the outer dark matter halo over billions of years. Dark matter in the outermost regions of a small galaxy is the least gravitationally bound component, making it the most susceptible to being torn away by a nearby massive neighbor. Supporting evidence for this general mechanism has been found in a second galaxy, NGC 105-2-DF4, where tidal debris is actually visible. Extended streams of stars being drawn toward a neighboring galaxy, NGC 1035, consistent with an ongoing interaction that has already removed most of the smaller galaxy's dark matter. Van Dokkum himself, in interviews after the 2021 distance confirmation, reframed the puzzle in terms that have stuck. The distance debate is now settled, and the scientific question has shifted to how these galaxies formed in the first place. The tidal stripping scenario explains how the dark matter was removed, but it doesn't explain how the galaxy formed the unusually large, very bright globular clusters that it has, with properties suggesting they formed in an unusual environment. A separate hypothesis proposes that these anomalous globular clusters formed during a high-velocity encounter between two larger galaxies, and that NGC 1052-DF2 formed from material ejected by that encounter. A bullet of gas that got separated from the dark matter in the original collision. This model makes specific predictions about the spatial distribution and velocities of similar dark matter deficient galaxies in the NGC 1052 group that are currently being tested with ongoing surveys. On the exact opposite end of the spectrum sits Dragonfly 44, also discovered by the Dragonfly telephoto array, located about 330 million light-years away in the Coma Galaxy cluster. Like NGC 1052-DF2, it is an ultra-diffuse galaxy, physically large but thinly populated with visible stars. But where NGC 1052-DF2 appears to have almost no dark matter, Dragonfly 44 appears to consist almost entirely of it. The velocity dispersion of its stars implies a total mass comparable to the Milky Way, roughly 1 trillion solar masses, but the visible stellar content accounts for less than 1% of that. The remaining 99+% is dark matter, making Dragonfly 44 one of the most dark matter-dominated objects ever identified. How two ultra-diffuse galaxies of similar physical appearance can occupy such wildly different positions on the dark-to-visible matter spectrum remains an open question. The galaxy formation processes that produce them may be completely different, or they may be the same process operating under different initial conditions. Either answer would be scientifically significant, and neither is yet confirmed. The galaxies that shouldn't exist, what JWST found in the early universe. For decades, the standard cosmological model made a specific prediction about the early universe. It should contain only small, chaotic, proto-galactic structures. The logic was built from well-understood physics. After the Big Bang, matter was distributed nearly uniformly, with only tiny statistical variations in density. Those variations grew over time as gravity amplified them. Denser regions attracted more matter, sparser regions lost it. Small structures formed first and merged into progressively larger ones. This is called hierarchical structure formation, and it has been spectacularly successful at explaining the universe's present-day large-scale structure. The model predicts that large, well-organized galaxies like the Milky Way took billions of years to assemble, building up gradually from smaller precursors. Then, the James Webb Space Telescope launched in December 2021, and within its first year of science operations, it began finding galaxies in the early universe that the model had not predicted. To understand why JWST can see these objects when previous telescopes could not, it helps to know something about how the universe stretches light. The universe has been expanding since the Big Bang, and as light travels through expanding space, its wavelength stretches. The technical term is cosmological redshift. Light from a galaxy that existed 500 million years after the Big Bang has been traveling for more than 13 billion years and has been stretched dramatically by the expansion of space during that journey. What left the source as visible or ultraviolet light arrives at Earth as infrared light. Previous infrared space telescopes were too small and not cold enough to detect this faint, highly redshifted light from the universe's first billion years. JWST has a mirror 6.5 meters across, roughly 3 times the collecting diameter of Hubble, and operates at temperatures a few degrees above absolute zero to suppress its own thermal noise. It was designed from the start to work in the infrared wavelengths where the earliest galaxies are accessible. What it found astonished the astronomers who built it. In 2023, multiple independent teams announced the discovery of galaxies existing just 500 to 700 million years after the Big Bang, when the universe was less than 5% of its current age, that appear to contain stellar masses comparable to the present-day Milky Way or larger. Astronomer Erica Nelson of the University of Colorado Boulder described her team's reaction in 3 words: "It's bananas." The standard model predicted that dark matter halos large enough to host galaxies of this mass simply would not have had time to grow yet. The process that enables galaxy formation, dark matter halos collapse at first, and drawing in ordinary matter requires time that the universe simply hadn't had. And yet the galaxies were present, confirmed by spectroscopy, the most reliable astronomical technique for measuring distances and physical properties. The deeper puzzle is not just that these galaxies are massive, it's that their stars are old. The spectral fingerprints of the starlight coming from these early overmassive galaxies show mature settled stellar populations. the kind you'd expect from a galaxy that has been forming stars for a long time. But the universe was barely 500 million years old when these galaxies are observed. There hasn't been a long time. Either these galaxies formed with extraordinary efficiency in a very short window, or the process of star formation itself was fundamentally different in the early universe than what our models describe. The most extreme individual case that has been studied in detail is a galaxy called ZF-UD-7329, examined by a team led by Carl Glazebrook of Swinburne University in Australia and confirmed through both Hubble and JWST observations. This galaxy is observed as it appeared roughly 11.5 billion years ago, just 800 million years into the universe's history. It contains more stars than the Milky Way. Its spectral fingerprints show old stars, not young ones. This means the bulk of the stellar mass formed even before the epoch of observation, perhaps 300 to 400 million years after the Big Bang, or possibly earlier. And then the galaxy stopped forming stars almost entirely. It quenched at an epoch when the entire universe was less than 1 billion years old. Quenching normally happens through one of several well-understood mechanisms. The galaxy runs out of cold gas. Something heats the gas so it cannot collapse into new stars. Or an active supermassive black hole drives energetic winds that eject gas from the galaxy. All of these processes take time, typically billions of years of gradual evolution. ZF-UDS-7329 appears to have formed a stellar mass greater than the Milky Way's and then shut itself down within the first several hundred million years of the universe's existence. Claudia Lagos of the University of Western Australia, a co-author on the key study, stated this directly. Having galaxies this massive, so early, poses significant challenges to the standard cosmological model, particularly around how they formed so fast and what caused such a rapid shutdown. The JWST findings don't stop at overmassive early galaxies, they extend to the structure of early galaxies as well. In December 2025, researchers Rashi Jain and Yogesh Vadadekar at the National Center for Radioastrophysics in India published the discovery of a galaxy called Alaknanda, named after a Himalayan river that shares its origins with the Mandakini, which is the Hindi name for the Milky Way. The name choice was fitting. Alaknanda formed just 1.5 billion years after the Big Bang, and JWST images taken through 21 separate filters reveal it already has two sweeping symmetric spiral arms wrapped around a bright central bulge, the classic grand design spiral structure associated with fully mature galaxies. Grand design spirals require very specific conditions to form. A gas must fall steadily into a rotating disk. That disk must remain undisturbed long enough to cool and settle. Density waves must develop within the disk and organize the material into coherent arm structures. The whole process was believed to take several billion years of calm evolution. Alaknanda accomplished it in less than 1.5 billion years from the Big Bang, in an era when the standard model expected galaxies to be chaotic, clumpy protostructures still assembling from scratch. The galaxy spans about 30,000 light-years and is building new stars roughly 20 times faster than the present-day Milky Way. It was only detectable in such fine detail because it happened to lie behind a massive galaxy cluster called Arbel 2744, whose gravity acted as a natural magnifying lens, bending and brightening the distant galaxy's light just enough for JWST to resolve its spiral structure. Wadada Carr described the implication directly. The early universe was capable of far more rapid galaxy assembly than anyone anticipated, and the physical processes governing how galaxies form appear to have operated far more efficiently in that era than present models account for. Alaknanda is part of a growing catalogue that JWST has been steadily building, galaxy after galaxy, from the universe's first billion years, showing structural maturity, stellar ages, and total masses that the theoretical framework didn't predict could exist yet. Some researchers have proposed that star formation in the early universe was simply more efficient than it is today, possibly because gas clouds were denser, cooler, or organized differently by turbulence. Others have proposed that the dark matter halos that seeded galaxy formation were themselves larger and denser than the standard model allows, due to subtleties in the physics of the post-Big Bang universe that haven't been fully accounted for. A third line of thinking suggests that some of these apparently overmassive early galaxies may contain unusually active black holes, contributing their own energy to the observed signal, making them look more massive than their stellar content alone justifies. None of these explanations has been confirmed. The James Webb Space Telescope is still early in its planned operational life, with decades of science ahead, and every new set of observations from the first billion years of cosmic time has added to the puzzle rather than resolving it. The universe's infancy is consistently stranger, more productive, and more organized than theory expected, and that gap between prediction and observation is where some of the most important cosmological work of the coming decade will take place. The Cartwheel Galaxy. Violence on a scale that creates new worlds. Not every extraordinary galaxy is mysterious because it defies explanation. Some are extraordinary because they demonstrate a process that is well understood and documented, and in demonstrating it, reveal something surprising about the relationship between cosmic violence and cosmic creation. The Cartwheel Galaxy sits about 500 million light-years away in the constellation Sculptor. Its name comes from its appearance, a large outer ring of brilliantly glowing stars connected by faint spokes to a smaller, more turbulent inner ring, all surrounding a disturbed, churning center. The total structure spans roughly 150,000 light-years, somewhat larger than the Milky Way. It has been photographed by every major telescope of the last several decades, and in 2022 JWST turned its instruments on it and captured the structure in more detail than had ever been possible, revealing layers of complexity that Hubble and earlier observatories could only partially resolve. What happened to the Cartwheel roughly 200 to 300 million years ago is one of the most dramatic events one galaxy can experience, a direct head-on collision. A smaller galaxy, visible in images to the right of the Cartwheel, still moving away from the site of impact, passed directly through the center of what was then a normal, rotating spiral galaxy. The intruder moved through so fast that it didn't merge with the larger galaxy in the way a normal collision does. Instead, its gravitational influence sent a ripple outward through the disk like a stone thrown into water, a compression wave that moved radially outward, sweeping up gas and dust as it expanded. As this density wave expanded outward, it created the conditions for star formation everywhere along its leading edge simultaneously. Enormous quantities of gas were compressed above the threshold for gravitational collapse. Stars ignited in a ring around the entire circumference of the wave at the same time, on a scale that a normal star-forming region couldn't approach. The result is the Cartwheel's brilliant outer ring, an active stellar nursery forming hot, massive, blue stars at a rate many times higher than anything in the Milky Way, spread across a ring tens of thousands of light years in circumference. What JWST revealed in its 2022 observations was the finer structure of this ring and what surrounds it. In infrared light, the telescope could see through the dust clouds that obscure the optical images, revealing the internal anatomy of the star-forming ring in detail. Dense clusters of young stars embedded in thick dust, streams of hot gas moving outward from the ring's inner edge, faint tendrils of material stretching between the inner and outer ring that weren't visible in the Hubble data, and the central galaxy's disturbed core actively rebuilding itself after the impact. JWST also detected large amounts of hot silicate dust, the same material that forms the rocky planets of planetary systems, being produced by the massive young stars in the ring and distributed across the structure. That detail carries a significance worth pausing on. The Cartwheel's outer ring is forming stars at an extraordinary rate due to a cataclysmic galaxy collision. Those stars are producing and distributing the heavy elements, carbon, oxygen, silicon, iron, that rocky planets require. Some fraction of those stars will have planetary systems, including rocky planets. On some subset of those planets, given enough time, conditions might develop that allow chemistry to become interesting. The Cartwheel is a galaxy whose violent history is, in a very direct sense, the engine of potential new worlds. What looks from the outside like cosmic catastrophe is simultaneously, on a longer timescale, the seeding of future complexity. The Cartwheel also shows something important about how ring galaxies differ from Hoag's object. The two structures look superficially similar, a bright outer ring around a central mass separated by a relatively empty gap. But their origins are completely different. The Cartwheel has a clear culprit. The smaller galaxy responsible for the collision is still visible in the neighborhood. The Cartwheel's nucleus is disturbed and asymmetric, still in the process of recovering from the impact. The ring is young and actively forming stars, not a long stable structure of old stars. The gap between ring and nucleus is not empty. It contains faint material still participating in the collision's aftermath. Everything about the Cartwheel tells the story of a recent known event. Everything about Hoag's object refuses to tell any story at all. The comparison illuminates a broader principle in observational astronomy. The same outcome can arise from very different physical processes, and telling those processes apart requires looking beyond the obvious visual similarities. Two galaxies can look nearly identical from a distance and have histories that have almost nothing in common. This is part of why understanding individual extreme galaxies matters, not just because each object is scientifically interesting in itself, but because each one forces astronomers to be more precise about the range of mechanisms that the universe actually uses to build the structures we observe. The Cartwheel is also a useful reminder that the most violent events in the universe are not exclusively destructive. The collision that produced the cartwheel's ring also produced an extraordinary burst of star formation along that ring's leading edge, one of the highest star formation rates of any galaxy structure in the local universe. Many of the stars being born in that ring right now are massive, and they are forging the heavy elements, carbon, oxygen, iron, silicon, that did not exist in the Big Bang. Those elements will be distributed through the galaxy and its surroundings. Some fraction will end up in future stellar systems and planetary formations. The cartwheel's violence is also the cartwheel's creativity, and both are happening simultaneously, powered by the same event. What extreme galaxies reveal about the universe itself. Stepping back from individual objects, these galaxies carry implications that extend far beyond any single object's peculiarities. Taken together, they form a kind of map of where our understanding is solid, where it has gaps, and where it may be fundamentally incomplete. IC1101's existence near the upper limit of galactic mass is not coincidental. The universe's accelerating expansion, driven by dark energy, sets a ceiling on how large a gravitationally bound structure can grow over time. The dark energy ceiling also explains why the record for the largest galaxy by stellar extent has likely not changed much in the past several billion years, and won't change much in the next several billion. New galaxies are falling into IC1101 and into other BCGs, but the infall is slowing as the expansion carries more and more potential material out of reach. The age of building the universe's most massive structures is effectively ending. Alcyonius points toward a different kind of limit, one set not by dark energy, but by the density of the environment a galaxy inhabits. The fact that a below-average galaxy with a below-average black hole produced the largest known radio lobe structure in the universe says something striking. The record for galactic extent is held not by the most powerful, most active, or most massive galaxy, but by whatever galaxy happened to find itself in the most thinly populated patch of intergalactic space and fire its jets outward without significant resistance. Scale in this context is determined more by environment than by intrinsic power. The biggest is not the strongest, it is the least impeded. The dark matter extremes represented by N, G, C1052-D, F2 and Dragonfly 44 expose a variability in galaxy formation that theory hadn't adequately accounted for. Standard models of galaxy formation treat the ratio of dark to visible matter as something that varies within a predictable range, more in some environments, less in others, but never approaching the extremes represented by these two ultra-diffuse galaxies. The existence of galaxies where visible and dark matter have been effectively separated, or where the dark matter dominates to the degree seen in Dragonfly 44, means the relationship between these two components is more flexible than the standard picture assumes. Whether that flexibility has implications for the fundamental nature of dark matter as a particle, its cross-sections for interaction, its behavior during mergers and tidal stripping, or whether it simply reflects the diversity of initial conditions and environmental histories that galaxy formation can produce, remains one of the genuinely open questions. NGC1277 offers something complementary, not a challenge to the models exactly, but a validation of one aspect of them while complicating another. Standard models predict that the compact, red, early quenching galaxies common in the universe's first few billion years should have been transformed almost universally by subsequent mergers and accretion, that almost none of them should survive intact into the present day. NG C1277 is the exception that confirms the rule by demonstrating the very specific and unusual conditions required to be that exception. Its survival is not evidence that the models are wrong. It is evidence that the models work, and that when you find a relic, it will almost always be somewhere with a very particular story to tell about how it escaped the fate of its contemporaries. The JWST discoveries carry perhaps the most fundamental implications. Hierarchical structure formation, the principle that small things assembled first, works across most of cosmic time, and there is no serious proposal to abandon it entirely. But in the universe's first billion years, something clearly allowed matter to organize itself faster, more efficiently, and more completely than the model predicts. The resolution to this puzzle will almost certainly require at minimum a better understanding of how gas converts into stars in the extreme conditions of the early universe, and may require revisions to assumptions about how dark matter halos grow during that period. It might also require something entirely new, a physical process or a cosmological ingredient that current models don't include at all. It's worth noting that this kind of discovery, finding that the early universe is more developed than predicted, has a precedent. When Hubble began its first deep field observations in 1995, pointing at an apparently empty patch of sky for 10 consecutive days, astronomers expected to find a few distant objects and mostly empty space. What they found instead was a sky full of galaxies, thousands of them, visible in every direction, back to very early times. The universe was richer, more complex, and more populated than even the most optimistic pre-Hubble predictions. JWST's discoveries follow the same pattern, at even earlier epochs and with even greater discrepancies from prediction. Each time the field has extended its reach into the universe's early history, the history has turned out to be more active than anyone expected. The galaxies at the extremes of size, strangeness, and age are not curiosities on the margins of astronomy. They are the places where the models are under the most stress, where observations push against the edges of what theory can account for, and where the most important new understanding will eventually come from. They are, in the truest sense, the frontier. The tools that made these discoveries possible. None of these galaxies were found by chance. Each discovery depended on a specific instrument built to extend human vision in a specific direction that previous instruments could not reach, and each instrument was conceived and built in response to a question that existing tools could not answer. IC1101's full extent, including the vast diffuse outer halo, only became measurable when large aperture telescopes combined with sensitive detectors could map its extremely faint outer starlight down to the few photon per pixel level. Alcyoneus was found in radio data from LOFAR, the Low Frequency Array, a network of roughly 20,000 individual antenna elements spread across multiple European countries, electronically connected to achieve the resolving power of a single telescope the size of a continent. LOFAR operates at frequencies that no previous radio telescope array could reach with comparable sensitivity, and the data processing required to assemble coherent images from its thousands of individual elements represents one of the most computationally demanding science programs ever undertaken. Marlin 1 was found by a researcher who invented photographic amplification techniques that could pull faint structure from photographic plates that had been sitting in archives for years. Techniques that were, at the time, a unique combination of chemistry, optics, and darkroom craft that nobody else had developed. NGC1052-DF2 was found by the Dragonfly telephoto array, which uses camera lenses instead of telescope mirrors, specifically because camera lens optics have far lower internal scattered light than mirrors, allowing them to detect the extremely faint, diffuse brightness of ultra-low surface brightness objects that conventional instruments would flood with their own internal noise. The JWST discoveries required an observatory that took 3 decades and $10 billion to build, a mirror larger than any space telescope ever flown, cooled to within a few degrees of absolute zero, placed at a gravitational equilibrium 1.5 million kilometers from Earth, so it stays permanently in the sun's shadow. Each of these instruments represents a different conceptual response to the same challenge. The universe contains things that are present but invisible to our existing tools. The challenge is to identify what would make them visible and then build the tools to do it. Every time this challenge has been met, with radio telescopes revealing jets and lobes that optical telescopes could not see, with infrared observatories penetrating dust clouds opaque to visible light, with low surface brightness optimized systems finding entire populations of ghostly, diffuse galaxies, with JWST looking back to within the first few 100 million years of the universe's history, the universe has shown something unexpected on the other side. This pattern is not just an interesting historical footnote, it is an active prediction about what is still out there, waiting. There are galaxies that no current instrument can detect, in wavelengths we haven't optimized for, at surface brightnesses below any threshold we've reached, in epochs that JWST can see but not yet fully characterize. The Vera C. Rubin Observatory, now beginning full operations in Chile, will survey the visible sky with unprecedented depth and cadence, detecting millions of faint, diffuse objects that existing catalogs have missed entirely. A new generation of extremely large ground-based telescopes, mirrors 30 to 40 meters across, will be able to resolve individual stars in galaxies at distances that are currently beyond reach. These galaxies are extraordinary, and they are also just the beginning of what those instruments will reveal. Every answer they have provided has generated more questions. Every record that has been broken has made clear that the records were only records because we hadn't looked far enough or faint enough or long enough to find what comes next. The universe does not give up its extremes easily, but it gives them up eventually to whoever builds the right instrument and points it in the right direction. There is something genuinely unusual about this field compared to many areas of science. The universe is not running experiments for our benefit, and we cannot go to the objects we want to study. Everything we know about IC1101, Alcyoneus, Hoag's object, NGC1052-DF2, and all the rest comes from photons, particles of light that left these objects millions or billions of years ago and happened to reach Earth. We have never touched any of these galaxies. We have never sampled their gas. we have only the light they send us, interpreted through the equations of physics that we believe describe reality, filtered through instruments of our own construction, and yet from that light we have been able to determine how many stars these galaxies contain, how old those stars are, how fast they are moving, what elements they are made of, whether dark matter is present and in what quantity, how long ago the stars formed, and whether the galaxies are growing or dying. The physics encoded in light and our ability to read it is one of the most powerful tools in the history of human inquiry. The fact that so many of the galaxies described here remain genuinely mysterious after decades of study with every available technique applied is not a failure of that tool. It is evidence of how deep the universe's complexity actually runs and how much work is still left to do. If this kind of deep exploration of the universe is what brings you here, subscribing is the best way to make sure you see everything we cover next. There is no shortage of cosmos left to explore,